the traveling salesman problem. Let's jump straight in. A salesman must visit 5 cities and return home. Every pair of cities is connected, and each connection has a cost. The costs are arbitrary. A 9 right next to a 2. The problem: find a cheapest tour. Visit every city exactly once and return to the start. First try around the outside. Total cost 20. A different order, a different total. This one crosses the expensive 9, 23. And this one weaves through the 2 cheap diagonals, 16, the best of all 12 possible tours. A tour is a cycle visiting every vertex exactly once, a Hamilton cycle. So the TSP asks for a minimum cost Hamilton cycle. 5 cities were easy. How does this scale? Count the tours, fix the home city, order the rest, ignore the direction. That's n minus 1 factorial over 2. 12 tours for 5 cities. For 10, nearly 200,000. For 20, beyond 10 to the 16th. Checking a billion tours per second, like this, 20 cities take 2 years. 30 cities take 10 to the 14th years, 10,000 ages of the universe. So brute force is out. Could a cleverer algorithm do it? Unlikely. Deciding whether a graph has any Hamilton cycle at all is already NP complete. The TSP contains that question, so it is NP hard. No polynomial time algorithm unless P equals NP. Exact answers are out of reach. Can we at least get close? New plan. Settle for a provably near cheapest tour. Here is what that means. An alpha approximation must do 2 things on every input. Run in polynomial time and return an answer costing at most alpha times the optimum. On a cost line, the optimum here, alpha times it there. The algorithm's output always lands in this window. A 2 approximation, say, is never worse than twice the best. Speed plus a guarantee, and the closer alpha is to 1, the better. For the general TSP, the news is brutal. Sahni and Gonzalez, 1976. If P is not NP, no constant factor is achievable. Not 2, not 100, not 1,000,000. The idea: take any graph, give its edges cost 1, and every missing edge 1,000,000 times n. A Hamilton cycle in the graph is a tour of cost exactly dirt cheap. No Hamilton cycle? Then every tour hits a missing edge, and the cost explodes. So even a 1,000,000 factor approximation would decide Hamilton cycles. An NP complete problem. For arbitrary costs, approximation is hopeless, but real costs are rarely arbitrary. Real costs behave like distances, and distances obey the triangle inequality. Going directly from U to W never costs more than a detour through V. With this property, we get the metric TSP. Do these 4 cities satisfy it? Check the triangles. Triangle U, V, W, direct 5, detour 4 plus 3, passes. Triangle V, W, X, 5 again 7 again, passes. The other 2 are the same. These costs form a metric. Read backwards. Cutting the stop at V only makes the trip cheaper. Shortcuts never hurt. 1 extra assumption, and a guaranteed factor of 2 becomes possible. Here it comes. 6 cities, metric costs, all 15 connections on screen. The double tree algorithm, 4 steps and a guarantee. The tour costs at most twice the optimum. Step 1. The cheapest way to connect all 6 cities, a minimum spanning tree, by Kruskal's algorithm. Cost 18. Step 2. Double every tree edge. Now every city has even degree. And even degrees mean the doubled tree has an Euler circuit, a closed walk using every copy exactly once. Walk it, out to C, back through F to E and D, and home. Length, exactly twice the tree 36. But it visits F 3 times. So, follow the walk, skipping anything already visited. A, B, F, C, nothing to skip yet. The walk returns to F, already visited. Jump straight to E instead. By the triangle inequality, that is no more expensive. 6, not 7. Then D, and from D, straight home. 7 instead of 15. A genuine tour costs 27, and we never compared tours. Runtime? Dominated by the spanning tree. Order n squared log n, polynomial. Recall, T is the minimum spanning tree we built at cost 18. Claim 1, T costs at most any optimal tour. Here is the optimal tour of this instance, cost 24. Delete one edge, say the most expensive. What remains is a spanning tree. Costs are non-negative, so that tree costs at most the optimum. And T is the cheapest spanning tree of all. So, 18, at most 19, at most 24. Claim 2, our tour costs at most twice the tree. The Euler circuit pays for each tree edge exactly twice. And the shortcuts only ever lowered that. Chain the claims. Tour, at most twice the tree, at most twice the optimum. 27, 36, 48. And nothing here was special to this instance. The double tree algorithm is a 2 approximation for the metric TSP. Thanks for watching. Hamilton cycles, Euler circuits, Kruskal's spanning trees. Each of today's tools has its own video on this channel. If you enjoyed this one, please like and subscribe. More graph theory is coming soon.